Hello, good evening. All right, all my WST students, welcome back to one more important session. Now, this time it is turn for your grade 11 students. What is that? We are going to do complete states of matter in one shot. Yes, students, this is the most important chapter for your term 2. Yes, I'm going to explain each and every topic. Yes, in a detailed way, I'll be explaining the whole chapter. Yes, detailed explanation would be there, and every line of NCRT would be covered here. So remember, students, every line of NCRT would be covered. And important thing is, please go through the video, take a notebook, note all the topics in your book so that you can get full marks in this chapter. Yes, students, let's start off with the chapter. Before that, let me see whether everything is getting recorded or not. 1 second, students. Yes, it is getting recorded. Let's start with the session. Very easy chapter. Let's go detailedly line by line. Before we start, these are the topics which are prescribed for your syllabus for your upcoming exams. So you're going to study about states of matter, what are the different molecular interactions. You'll be studying about, rather what bonding, what actually is melting and boiling points, everything rather one topic will be studying. And from there we'll be going into the gas laws. These are the gas laws. We'll be studying about deviations in your from the ideal gas equation, what are real gases, what are ideal gases, what is Avogadro number, everything like that. So hydrogen bonding, everything we are going to study today. Let's start with the chapter. So before that, please, my request, students, please like the video. It's very important for WC. Comment whatever you felt after watching the video. Share the video to your friends so that it is free of cost, nothing. It takes 2 seconds to share. It's free. Please subscribe to the channel, inform them. 100% syllabus is done on WC. 1600 videos are there for grade 10 students, grade 11 students, grade 12 students, and JE as well as NEET students also. And thanks for watching, students. God bless you all. Let's start off. The first thing before we start the chapter, you should know what actually is matter means. What does it mean? See, you're able to see different forms of matter. Let it be in the solid state, let it be in the vapor state, let it be in the form of air, rather, let it be in the form of gases. So everywhere, whatever is there, matter is nothing but, yes, it is nothing but, it is a form of mass, or rather, matter means mass, correct? That mass which occupies space, correct? Matter is nothing but mass which is going to occupies space. Any substance on this earth which has mass and which occupies space is called matter. Easy. Okay, this is mass, this is occupying the space, this is mass, this is occupying the space, this is mass, this is gold biscuits which is occupying space. So anything which has mass and occupies space is called matter. All right, what are the different states of matter? States of matter basically are of 5 types. What is that, students? First state is nothing but solid state. Yes. Second state is nothing but, yes, you said it right, liquid state. Third state is nothing but your gaseous state. Correct, students? Gaseous state. Okay. Fourth one is what? Fourth one is nothing but plasma. What is the fifth one? State, which is found in the stars, is nothing but Bose-Einstein condensate. Correct, na? Bose-Einstein condensate or Bose-Einstein state. Condensate is one more state. So, 5 states of matter are there in us. So first, before we start the chapter, let us know the difference between solid state, solids, liquids and gases. Easy, students, this is grade 10 syllabus. Let's see. So when we know solids, first important thing, solids have definite volume, correct? They're fixed volume, correct? Liquids also have definite volume. How, ma'am? Because this definite volume, when I say, means they are going to take the shape of the container, correct? Na? Whichever shape, suppose if you're pouring it in a jug, it will take the shape of the jug. If you pour it in a glass, it will take in the form of a shape of a glass, correct? And gases, no definite volume. There is no fixed volume. Why? because they have diffusion process. They keep moving continuously, they keep flowing in the air. Correct? Right. So when I talk about the shape, same thing. They have definite volume is definite. Here shape also is definite. Now, as I said, liquids are going to take the shape of the container. Correct, na students? Right? The same thing as above. Whichever shape you're taking, if you're taking a glass, they're going to take the shape of the glass. Very bad glass. If you take a big tumbler, it'll take the shape of the tumbler. Correct? If you take any sort of round shaped container, that takes the shape of a round shaped container. Correct? That's so no, so you'll be writing the same shape of the container, same thing as above, do shape of the container. Here for gases, we very well know there is no definite shape because they have their diffusion of gases. It keeps flowing when it is in the open air. And when I see solids, they have very strong forces of attraction. Strong forces of attraction they have among them because they are tightly packed. Correct? Here, the force of attraction between liquid molecules because they're very far away like this. Na? So the force of attraction is what? Forces of attraction are moderate. Attraction are moderate. I'm writing a little bit small. Are moderate in nature, little bit because there are gaps in between. They're moderate. Here in this case, the forces of attraction, if I say, yes students, they see they it's very far and far. If I say liquids, it is so much. When I say gases, gas molecule is here, one is here, one is here, like that. So maybe I'm covering the picture, so I'm writing here the forces of attraction of the gases is nothing but very far. So the attractions are less and they flow very far. Attractions are less and they flow. The tendency to flow is more. Correct, na students? So strong forces of attraction here. Forces of attraction are moderate in liquids and attractions are less in case of gases. More further, we will write solids are very hard. Correct. Liquids, they tend to flow. Okay, they're going to flow because they have less gaps, there are more gaps in between the molecules or the atoms of molecules. And in case of gases, this gases, they're going to change according to what? The tendency of the gas changes according to the more pressure you apply, the tendency changes. What happens? Compresses. If you apply more temperature, what is going to happen? It will move farther and far away. Correct, na students? Yes. And next, solids are very rigid. Very rigid. Correct now? Suppose if you apply force on solids, suppose you're applying force on this, force on solids. If you're applying like this, you're applying force on this particular solid, what will happen students? That solid from rigidity, it will become deformed. It's going to change its shape. Correct now students? So they're very rigid and right. And if I have to say, so liquids are not much rigid, so and gas is also negligible. If I take different examples of this, you can write different metals: copper, silver, gold, platinum, salts, ice, different examples you can write. So liquids, you can write different examples like milk, water, yes students, oil, alcohol, all these are different examples. So in gases, when you take any gas, you can take like helium, like neon, like hydrogen, like nitrogen, oxygen, etc. and etc. Easy. So the differences between solid, liquid, and gases are easy. Okay. Now, first we are going to study about a concept called intermolecular forces. So basically, we said there are three types of states of matter, correct? So we have solids, we have liquids, and we have gases. Now, what are intermolecular forces? The forces of attraction between the molecules. Of course, intermolecular forces, solids in between the solids, whatever forces of attraction are there inside the solids like this. Liquids, if I take a little bit far away, little gap, little gap, little gap. And in gases, when I take this very far. So intermolecular forces are nothing but, if I have to tell you, forces of attraction or forces between molecules. B by W means it is nothing but between molecules, forces between the molecules. Got it? There are basically four types. What are they, students? First type of intermolecular force, do I have space? Okay, I'll write here. First type of intermolecular forces, London forces. Okay, London forces, the other name given is dispersion forces. London forces are dispersion forces. Is it okay? Done. The next important thing is dipole-dipole force, dipole-dipole interactions, or the forces of attractions or interactions. Next is what? Third one is dipole induced dipole. We are going to learn about all these one after the other interactions. The last one is nothing but hydrogen bonding. Okay, students? All right. So four different types of attractions would be there between the molecules of solids, between the atoms, between the molecules of these particular things. Let us see this. Let's see. First one, when I see dispersion forces or London forces. And most important thing, these are the weakest forces which you have to. These are the weakest forces. Why this is the weakest force? Why? Because these forces are formed between non-ion interactions. That means, let us see. When I take an example of this, now you're able to see, students, it is formed between two atoms. Correct, na? Both don't have any ions. Yes. So two atoms combine together to form a molecule. Yes, students. So what happens at any instant of time, at particular time, any instant of time, what happens? The electron cloud of these atoms, it get disturbed. Yes, it get disturbed. The electron cloud of this atom and electron cloud of this atom get disturbed. So electron cloud gets disturbed. Okay, so what happens when the electron cloud gets disturbed? Automatically, what happens, as you see, there is an instantaneous or induced dipole. Instantly, there is a pole. Two poles are created on that. Yes. So because of this getting disturbed, there is a formation of instantaneous or induced dipole. Induced dipole. Instantaneous or induced dipole means two. So this is between two opposite things which you are seeing when it is positive and negative. So because of this, the forces, whatever they are attractive, students, forces are attractive in nature because both are positive pole and negative pole. Done. One proton here and an electron there. Easy. So, and this is okay. But what happened here is these forces are working over short distances, small atoms, no? So work only at short distances, very because it is temporarily created. Yes, work over very short distance. When you move this one particular atom far away, it will not attract. So here, this particular London dispersion force. So what important thing here is these forces, whatever are there, they are going to depend upon what? They will depend upon number of electrons, what are there inside. They will depend upon molecular structure, what is there here, whatever structure is there depends because size should remain, electrons how many are there it counts, how far they are there it counts, correct? And polarizability of particles, how much it is polarizability, how much it is going to drag the particles, that is also is what matters in your London dispersion forces or the weak forces. Yes, so and most important thing apart from all, distance. Yes, distance also matters, students. How much is the distance? So number of electrons it counts, molecular structure it counts, polarizability of particles, how much it is going to drag the charge, and distance also it counts. So these are all the interaction part. Because of this, because when you pull them ahead, the attraction is lost. That's why they are called weakest force, and they are also called as non-ion interactions. Do you have any ions? No, it is only between two atoms which are formed. So they are also called as non-ion interactions. Easy? Easy. Let us see one more. Dipole forces, right? So when dipole forces, when you see, the first important thing, see here, you have a positive charge on one side, you have a negative charge. That means dipole forces, they occur in polar molecules. They occur in which molecule? Polar molecules. Done, students? Done. Because they occur in polar molecules, see here, you have one HCl molecule here, one HCl molecule. Negative attracts the positive thing, positive attracts the negative. So there are two different poles which are created. So these poles are called what? They are called dipoles. Di means two, opposite. So that's why these dipole-dipole interactions are always permanent dipoles. They are created between oppositely charged species. Yes. Here positive pole, that is your H plus, attracts your negative pole, that is nothing but Cl minus. So both of them get attracted. And remember students, the interactions whatever are there in dipole-dipole, they're very strong. Interactions are stronger in nature. Remember, they're very stronger compared to the earlier. Yeah. Yeah. One more, dipole induced dipole. Now see students, here able to see there is one polar molecule here and a non-polar molecule here. Yes. For example, this non-polar molecule is an inert gas. Inert gas. Just like your helium, neon, argon, krypton, all the inert gas. Inert gases will not participate. They will neither donate nor accept, except few exceptions. So, inert gases like this or any noble gases, when they combine with a polar molecule, we get dipole-induced dipole forces. Means, for example, you have a polar molecule and you have a non-polar molecule. In the presence of this is going to induce a charge on this inert gases. Got it? Right? That means dipole-induced forces are non-polar molecule getting polarized. Getting polarized. It is going to get polarized or charged. Rather, non-polar molecule which doesn't have any charge will get polarized. Got it, students? Okay. So here, because of this polarization, temporarily there is an induced dipole, two poles which are created in the inert gas. Which one made this? Because of this. Because of this, when you rub both of them or get together, just like a sort of, charges created. Like that, both of them, when they come together, there is a sort of induced dipole created. So what factors are dependent on this? Yes. Important thing, distance between molecules. Okay. Your distance between your molecules, what matters first. More far they are, this attraction is less. More closer, immediately the dipole can be created. Correct. Next important thing, this depends upon dipole moment of polar molecule. Dipole moment of which one? Of polar molecule. Whatever polar molecule is adjacent to that, that also depends, because this has to create or induce dipole in this. Correct? So, dipole moment of polar molecule also is important. An important thing, polarizability of non-polar molecule. How much your non-polar molecule is responding, how much you're giving it charges or inducing the charges. So polarizability of non-polar molecule also is important. That means here polar would be there, inert gas would be there. Inert gas is going to induce the charges in that, and you are going to see that distance you have to maintain. You have to see the polarity of the polar molecule and how much you are creating charge in the non-polar molecule. Polarizability means creating the positive charge and negative. No, if I have to tell you polarizability, the drag of this charge. See here, this is negative. It's going to polarize this part positive end, and it is going to drag it like that, just like a Fajan's rule which you have seen. So these are the factors. Let us see one more. Hydro. Okay, this part is done. So important thing. What should I remember? In dipole dipole induced dipole, what is important students? I require a polar molecule which is going to polarize. Okay, which will polarize which one? Non-polar molecule, just like your inert gases. Yes. And the distance is important, dipole moment is important, as we have seen. See here, dipole moment is important of the polar, and polarizability of the non-polar molecules is important. Okay, let us see the next one, hydrogen bonding. Okay, right. So hydrogen bonding is basically a special case of dipole moment. It's a special case of dipole interaction. Okay, special case of dipole interaction. What is this? So remember, students, hydrogen bonding is formed between oxygen and hydrogen. It is formed between fluorine and hydrogen. It is formed between nitrogen and hydrogen, remaining all the same. Yes, that means hydrogen bond is formed between oxygen and hydrogen, nitrogen, or rather hydrogen and fluorine, and nitrogen and hydrogen. And always remember, hydrogen bonding is denoted by dotted lines. Dotted lines. So when you dissolve it in water, the bond formed between the oxygen atom, fluorine atom, and nitrogen atom, just like what we call it as Fon atoms. Fon means fluorine, hydrogen, fluorine, hydrogen, oxygen, hydrogen, nitrogen, hydrogen. So these are the, so here this hydrogen bonding basically is found in which molecule? Is found in highly polar molecules. Highly polar means charged particles, rather ions. One electronegative atom and electropositive atom. So polar molecule, right? In you can also see it in chlorine also stored. Oxygen, hydrogen, hydrogen, fluorine, nitrogen, hydrogen, hydrogen, and chlorine also. Some cases. So what is the use of this hydrogen bonding? Hydrogen bonding, I can use it to explain protein structures, which have hydrogen bonding, nucleic acid, just like your DNA, RNA structures, everything I can explain using this hydrogen bonding. Yes? All right. Now, if I see the types of the hydrogen bonding, there are of two types. Intramolecular hydrogen bonding and intermolecular. Intra means what, students? Intra means within the molecule. Within the molecule. Okay. Inter means between the molecule. Okay, sorry, this is in this is wrong, students. This is inter, wrong. This is inter, I'm sorry. This is intermolecular and this is intra, right? So we have written it wrong. I'm really sorry. This is wrong, students. Just check. First thing is intermolecular. I'm sorry. Intermolecular hydrogen bonding means in between the molecules. In between. It is between two molecules. In between two molecules. Got it? And intramolecular means it is within the molecule. It is within the molecule. Okay? Within the molecule. It is within means inside. Inside. Intra means inside the molecule. Okay, so let me little bit erase this for you so that you will not get confused. One second, students. Let me take the one second. Let me shift the camera eraser. Let me take this out. It should not confuse you all. So we will write, and we will take the pen and make this as inter. Okay, now right. Let me adjust the camera once again, please. Okay, right. This is okay. This is intermolecular. Next important thing, we are going to study about a concept called thermal energy. Okay, what is this thermal energy? Yes, see students, remember, thermal energy is basically, just check, atoms are there in a particular thing. This atom, this atom, this atom collides with this atom collides with this atom collides with this, or molecules also, correct, na students, right? They collide with this one more is there, this collides with this one more is there, this collides with this, right? Thermal energy is an energy released. Okay, what is this? Thermal energy is an energy released due to what? Energy released due to motion of, this is important, due to motion of what? Motion of either atoms or motion of molecules. Movement of atoms or movement of molecules. So important thing to remember before we start the differences, important thing to remember, see here, thermal energy, TE means thermal energy, is directly proportional to temperature. More temperature you give, more movement will be there in the atoms or molecules. Got it? Next. This thermal energy is, if I have to say, it is an average of all the kinetic energy, students. How did I get? Thermal energy is an average of all kinetic energies of the particles. Means like vibration energy, translation energy, mechanical energy, like that. All the combinations together is a thermal energy. So we call this as thermal motion also because of the movement of the particle, like translation, vibration, mechanical, all these together, we call them as thermal motion. Okay, thermal motion, thermal motion. Got it, students? Yes. Now we are going to see what actually is the difference between intermolecular forces and thermal energy. So yes, we get confused, na? Yes. Now see here. Intermolecular forces, if I have to write, intermolecular forces. So every time I will not write full, I will write it as IMF. Intermolecular forces are what? Basically, they are forces of attraction between molecules of a substance. What are they? Forces of attraction between molecules of a substance. Whatever molecules are there, that forces of attraction in a substance, whatever molecules are there, those attractions are called intermolecular forces. Now, what is thermal energy? Basically, thermal energy means the energy possessed. What is that? Energy possessed by the molecules. How? Because they move continuously. Na? They inside whatever are the energy possessed, whatever energy is possessed inside, whatever total energy, what molecules are there here, like this. Suppose if you see, okay, let me take this. Okay, you have this particular substance, inside you have molecules. Whatever energy they have inside this, energy possessed by molecules. How did this energy come? Due to motion. Due to increase in temperature. When you increase the temperature, the molecules start moving. Na? So one molecule moves like this, one molecule moves. So energy possessed by the molecule due to increase of temperature, and molecules start moving far. The molecules start moving far. Students, so this is called intermolecular forces. Now, let me drink some water. So we are going to see the difference between these two. See here. So intermolecular forces, thermal energy. So now I know it is the force between the molecules of a substance. Thermal energy is nothing but the energy possessed by the molecule when they start moving. When you increase the temperature, when they start moving, that's the thermal energy. If I talk about the solid state, let us talk about one state. Here also we will talk about solid state. Correct? SD means solid state. Solid state. So in solid state, very good. Just say intermolecular forces IFA, intermolecular forces of attraction means IFA, are much more than thermal energy TE. Why? Because solids have rigid structure. Correct, my students? The very tight structure they have. That's why in IFA would be more in thermal energy. Now in solids, basically thermal energy, what happens? Suppose you're increasing, you're heating it. Delta means you're heating, or you're increasing the temperature. Temperature is increased. Then what will happen? Molecules start breaking. Molecules, whatever are there, the molecules start moving apart. Means they will move apart, right? Then what is going to happen? Solids, they are going to get converted to liquids because you're increasing the temperature. Na? Here, whatever was there, first solids were very tight like this. You started increasing the temperature. Now one solid becomes here, one goes like this, one goes, and they'll become a liquid. Solid gets converted to liquid. Correct, students? Now, second one. Let me take liquid state. Okay. Here also let me take liquid state. What happens? Liquid state, intermolecular forces of attraction are equal to thermal energy. Here also same, intermolecular forces of attraction are equal to thermal energy. What is the reason, students? Tell me. The reason here is, yes, in liquids, the molecules are continuously moving, correct? So let me write the same reason for both. continuous movement of continuous movement of particles, liquid particles rather. Correctness, when liquid particles are continuously moving, it's liquid state. This is the case. Suppose if I go with gaseous state, let me take gaseous state here. GS means gaseous state. Here also GS means gaseous state. Okay, right. Now what is going to happen? Gaseous are the diffusion is more, correct na? Yes, students. Here what happens? Here what happens? When intermolecular forces increases, because this I said diffusion, because they move very far, the distance is more, attraction is less. So when the intermolecular forces are increasing, what will happen? Thermal energy also increases because they're moving very far. One is moving here, one is moving here, one is moving here, one is moving here. Yes. So what is going to happen? Solids will get converted to liquids. Liquids will get converted to gases. Means basically the diffusion is more. But in case of gaseous state, remember, thermal energy is very much greater than intermolecular forces. Why? Why? Because gases are compressible. Correct? I can compress the gas. When I compress the gas, intermolecular forces are decreasing. AMF, AMF is decreasing because when you're compressing, intermolecular forces are decreasing. Correct? Na? Or decreasing. Because when you're applying pressure on something, what will happen? All the gas particles will get come closer. That's why the IMF forces or the intermolecular forces are decreasing. Correct? Na? That is what is thermal energy in case of students. Easy, right? So you should write regarding solids, you should write regarding liquids, you should write regarding. Now when I start with the gaseous state, very important. After your basic thing, let's start. Gaseous state. Now first we will write the physical properties. Okay, I learned about all the intermolecular forces and I have learned the differences between thermal energy and intermolecular forces. Now we will learn about gaseous state. Now let us see the properties. Gases are highly compressible. Okay, I can compress the gas so that the intermolecular forces decrease. And gases, what do? They exert pressure in all directions. Correct. All directions they are going to exert pressure from all the directions. The gases move in this direction, the gas particles move in this, they move in this direction, they move in this direction because they have the property of diffusion. An important thing, yes, gases have low density. Correct, na? They are very low density compared to your solids and liquids. Correct, na, students? Why? Because they move very far. This one, if you consider this as a room, if you release a gas, the gas particles attraction is less, na? So the density is equal to mass by volume. Automatically, when they diffuse, there is nothing particular mass which is there with that. Right? And for gases, volume and shape not fixed. Correct? It is not fixed because what do? They take shape of the container. They are going to take shape of the container. It is not fixed. Okay, done. Now we are going to see the different gas laws. What are the different gas laws? You are going to learn the first gas law, that is nothing but Boyles law. Okay. This Boyles law is also called as PV relationship. You're going to study the PV, pressure volume relationship. Second type of gas law is called Charles law. This is called temperature volume relationship. That is PV, this is TV relationship. TV relation. Third type of gas law is called Gay-Lussac's law. What is it? Gay-Lussac's law. This is called PT relationship. PV, TV, PV, TV, and PV, TV. This is a relationship, PV, TV, and PV, TV, and PT relationship. Whenever you're learning this, any of these three gas laws, you should learn important things. Under Boyle's law, you should learn what is PV relationship. You should learn what is the relationship in pressure and density. You should also learn what is meant on the graphical representation. Right. When you are learning Charles' law, you should learn VT relationship. You should learn what is the relationship between VT and V0. You should also know what is graphical representation. Okay, graphical representation, and you should also learn what is meant by absolute temperature. Got it, students? All right. When you learn Gay-Lussac's law, you should learn what is PT relationship. You should learn what is graphical relationship. Graphical relationship. Okay, let's start. So, first thing, in your gas laws, we are going to learn one after the other. As I said, gradually, slowly, we will learn and see. There is one more law called Avogadro's law. Fourth law is Avogadro's law, and this Avogadro's law is called volume amount relationship. What is it? Volume amount relation. We are going to learn about this. Apart from this, in the gas laws, you're also going to learn ideal gas equation. Ideal gas equation is also called as combined gas law, and you will learn like a concept called ideal gas equation in terms of density. In terms of density, you'll be relating it. We will see that also. We'll be learning about behavior of real gases. Behavior of real gases, and we are going to learn deviation from ideal gases. How these are going to deviate from ideal gases, we have to see this. Right, students? Let's start. First important thing, Boyle's law. What is the other name? It is also called as PV relationship. What is it called? PV relationship. Right. What is the definition? So, definition is, see here, whenever we are considering any particular gas, standard conditions, we'll be talking in terms of pressure, temperature, volume, yes, students, and number of moles. These are standard conditions. So we'll be keeping one as constant, the other two will be variables. So in case of Boyle's law, at constant temperature, okay, the temperature is kept constant, pressure of fixed amount, fixed amount means number of moles. Number of moles is fixed. Pressure of fixed amount of gas is inversely proportional to volume. Okay, what did we write? What did we write? We have written pressure of the gas is inversely related to volume. What are constants? So two are variables. N, number of moles, and temperature are constant. Yes. So what are you going to do? You're going to take out this proportionality constant. P is equal to K into V. PV is equal to K. So PV is equal to K is your Boyle's law. So this is one Boyle's law formula. This is one more formula. Got it? Right. You took out the proportionality constant. Now, important. So we said product of the pressure. So let us write one more definition of Boyle's law now. Product of pressure and volume of a gas or a fixed amount of gas. Fixed amount of gas. That is nothing but number of moles N at constant temperature. At constant temperature is always constant. Is always constant. That is what we have written. One more definition. That means PV is equal to K is Boyle's law. Got it, students? Yes. Suppose if I take for gas 1, here N is fixed, number of moles is fixed here, right? So just that means that N value you're allowing the gas to expand, but number of moles are same. So let us take one more gas. Here also same N is fixed. Now you are allowing this gas to expand. Allow it to expand. Allow it to expand. This also you're allowing it to expand. When you allow it to expand, what will happen? PV will change from P1V1, which is equal to P2V2. When you are allowing it to expand, both, right? And here N and T are constants. Both N and T are constants in this case. So it will become into a new pressure P1V1 is equal to P2V2, right? Now let us see the relationship between pressure and density. Okay, see here, density is equal to mass by volume. I'll take out this volume outside. Volume becomes mass by density. Yes. So I'm taking this value and putting the value in Boyle's law. See here, what is Boyle's law? Boyle's law for me, I have got it as PV is equal to K prime. Now instead of V, try to substitute this Pm by D is equal to K prime, new constant. Yes. Now we said in Boyle's law, mass is constant. That means number of moles is constant. Now, what is this? How is this related? We know number of moles is equal to mass by molecular mass, given mass by molecular mass. That's why both are directly related. That's why you can neglect this factor m. So what will happen now? P is equal to, neglect means keep it in constant. K prime D, done. Yes. Okay. Now pressure is equal to K prime D. This is one pressure density relationship. So according to the earlier one, P1 by P2 is equal to D2 by D1 by D2. D1 by D2. We have this formula, na? P1 V1 is equal to P2 V2. So instead of that, I have made it into density. This is one more formula relating your density. Done, student? Easy? Easy. Now, let us see the graphical representation of Boyle's law. Okay, we have three different laws. What is that? Remember, first, according to the first law, careful, when you plot a graph between P versus V, Vp versus 1 by V, you will be getting a straight line passing through origin. Straight line through origin. You will be getting a graph which passes straight line through origin. You will see that. Second, you are plotting a graph, PV graph. You will be getting a hyperbola. Hyperbola. Okay, this is called isotherm. Why? Because you're keeping temperature constant. Temperature constant. Third graph is PV versus P. You will be getting a horizontal line. Horizontal line which you'll be getting straight. Straight line which you'll be getting. Let us see all the three. Check. First one. I'm going to draw the first graph. Graph number one. Graph number one, which is nothing but pressure versus 1 by V. Sure. First of all, let us assume a concept like this. See this. I am taking pressure. I am taking volume because since PV is equal to K, constant. Let's see. I am considering pressure, I am considering volume and constant. Let's see. Suppose, this is quite common example. Pressure I am taking 1 atm. Okay. Now volume I am taking 100. Got it, students? Yes. Now this is constant. So basically 1 into 100 is 100. This is constant value. Constant means it should be all 100 only. 100 only. So see here. In the second case, I'm increasing pressure 2. This will become 50. Why? It every time the pressure is PV is equal to K constant. That's why this constant value 5 into 2. Suppose I'm making it 4. 25. If I'm making it 5, 20. Everything, all you multiply together, it should be 100 only. Like that, you're increasing little more little. So, pressure is constant. Now I'm plotting a graph. sorry, very bad line, plotting a graph. First, I am taking pressure in x-axis, 1 by V on y-axis. Okay. Now see here. First 0. उसके बाद 1 atmosphere, 2 atmospheres, then 3 atmospheres, 4 atmospheres, 5 atmospheres, 6 like this. Now observe, I have to calculate 1 by V, 1 by V. So make 1 by 100. 1 by 100. How much is this? 0.01. Second, make it 1 by 50. How much is this? 0.02. Next, 1 by 25 is 0.04. Like that, I'm going to calculate 1 by V value. So I'll make this as 0.01. I'll make this as 0.02. Like that, I'll be making one line like this for 1 by V. So plot it. So when the P value was 1, how much is volume? P value was 1 atmospheres. How much was volume? 0.0. When it was 2, how much was the volume? 0.02. When 1 by 25, or rather when it was 3 atmospheres, it was 3 atmospheres. Gradually it was like that. You are getting a graph which is passing through the, you're getting a straight line graph which is passing through the origin. Yes, because I'm drawing with my writing pad, the line is not straight, but in PV graph, what do you get? You get a straight line graph which passes through origin. Easy, students? Easy. Let us see one more graph. This is graph 2. In graph 2, you're going to draw a particular graph where PV is equal to K. That means, let's see, I'm making one pressure, volume, and K. Same thing, one constant means the value should be all equal. So 1 into 100, let us assume volume is 100. So let us make 100. Constant value I have set 2, then volume becomes 50 into 200. 4 into 25, 100. 5 into 20, 100. Correct, na students? Yes. So in this case, what is kept constant? Temperature and number of moles are constant. So draw a graph now. Draw a graph. Make one line, a y-axis. Make one x-axis. Pressure is on the x-axis. Volume is on the y-axis. Now see, how much was pressure? 1, then 2, then 3, then 4, then 5. Here, how much was it? Let us start 10. Next is 20. Next is 30. Next is 40. Next is 50, like that. Now you see, when pressure was 1, like that, 50, 100, 100 also here, because there's no place. When pressure was 1 atmosphere, the volume was 100. When the pressure was 2, the volume was 50. When the pressure was 3 or pressure was 4, the volume was here 25. Like that, when I measure, I'll be getting a graph which is nothing but, join this graph, very bad line. This graph is nothing but hyperbola. Hyperbola. So a PV graph which you're getting is a hyperbola at what concept, students? At constant temperature. That's why this graph is called isotherm. Isotherm. Got it? Yes. Right. Let us see one more graph. This is graph 3. Graph 3. Right? In this case, same thing. PV is equal to K. 1 pressure, 100 volume. I kept constant as 100. 2 pressure, 50 volume. 4 pressure, 25 volume. 5 pressure, 20 volume, like that. Right? Now what are you going to do? I'm going to plot a graph where I'm going to plot between PV versus P. Got it? So how does it go? Pressure is 0 here. Here if I take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. On the y-axis, how much was this? PV is constant at a count of 100. Na? So I'll make it as 50, then 100, then 150, like that, 150, like 200, 250. Now see, when the pressure was 1, how much was PV? 100. When the pressure was 2 atmospheres, yes, 50 into 2. See here, when the pressure was 2 atmospheres, 50 into 2. 50 into 2. It was 100 only. Again 400, it was 400, 600, 500, like that. Everything is 100 only. So that means PV graph is PV is equal to K. Nothing, students. See here, when the pressure was 2, how much was PV? P into V is 2 into 50. Got it? So here, in this case, it is a straight line. It is a straight line graph. You see? Okay. Before we go to Charles' law, one more this there. And suppose if your teacher is asking you, yes, students, there's no place I'm drawing here. See here, one more graph is there, where if you're plotting a graph between P versus 1 by V, right? You've got one first figure, na? Let us go to the first figure there only. See here, you've got this graph, na? Here only I'll draw. Here only I'll draw. So P versus 1 by V, you're performing this experiment, you'll be getting a straight line passing the origin. So you'll be getting a graph something like this for different temperatures. Different temperatures, because the temperature, rather, you're performing, I mean, you, different temperature, mean temperature keeping constant. For different examples, you're changing the pressure and volume. So you'll be getting this is T1, this is T2, this is T3, this is T4. Now you only tell me how would be the temperature, students? Yes, always remember T4 is higher than T3. Correct? Yes, right. So T4, according to Boyles law, temperature 4 is greater than 3, greater than 2, greater than 1. See the values. Right. Let us go to the next law, that is nothing but Charles' law. Right. Let us see. Charles' law is also called as TV relationship. TV relationship is what is this? So what is the definition of Charles' law? Definition says at constant pressure, volume of a gas is directly proportional to absolute temperature. What is it? Volume of the gas is directly proportional to absolute temperature. You will see what is absolute temperature. At what is constant? At constant pressure. That's what is important. So you take out the proportionality constant, V is equal to KT. V by T is equal to K. So this is one Charles law thing, formula and derivation, and this is one more Charles law derivation. So see here, how did we get this? See here, PV is equal to nRT, one ideal gas equation. So isn't it V directly proportional to T? That's all. It's simple. Right. This is your Charles law. Done. Now this graphical representation of Charles law, when you do check here, you see you're plotting a curve between volume and temperature. You said just now V is equal or directly proportional to K into T. When volume increases, temperature also increases. When volume increases, temperature also increases. Volume increases, temperature. Volume increases, temperature also increases. So what are you going to get? You're going to get a straight line, very bad line. Oh, sorry. Sorry, student. Very bad. So I should not take like this. I'll make like this. A straight line passing through the origin. Very bad line. So let me erase this once again because it is looking so dirty. Okay. So let me take. All right. Let me draw one straight line for you all. I'll try to do it. Okay. So you'll be getting a graph which is straight line passing through the origin. Something like this. Both are directly related. Correct, now students? Yes, both are directly related. So I'll be getting a straight line passing through the origin. You see? Right. Now see. And whatever is the slope here, this is nothing but K. Correct? How did you do this here? PV is equal to nRT. Correct? V is equal to nR by P into T. Correct? Yes. Now see here nR by P, according to this, nR by P is nothing, like I shifted the values. That is okay. Right. So this is one formula. Let us see one more. V is equal to K into T. Yes. Now this K is nothing but the slope. That's a slope. K is a slope. Okay, we know this. V is equal to K into T. We know this. This is also one more. Now V is nothing but K into slope. It's nothing but slope. Now you see in the slope, pressure is in the denominator. Okay, pressure is in the denominator. That means it's in the denominator means, see, how did I get y is equal to mx plus c? Mx plus c. So m is nothing but the slope. Slope is nothing but nr by p. P is in the denominator. That means when I draw these graph, V is equal to T at different pressures. Let me draw one more. One more. One more pressure. All passing to the origin, students. One more. So P1, P2, P3, P3, P4, P5 I draw. If they ask you what is the order of pressures, always remember according to this formula, see here, V is equal to nR by P, where P is in the denominator. That means P1 is less than P2 less than P3. Got it? So pressure is decreasing. That means when your slope is more means pressure decreases. This is what is the concept. Done? All right. Next one, students. Absolute temperature. Right. What is this? See here, students. This is your absolute temperature. This one. 0 Kelvin is the absolute temperature. So first of all, what is this absolute temperature? Let us define. So see here, students. Yes, absolute temperature, this one what you extended, it's the hypothetical lowest temperature. Okay, the hypothetical lowest temperature where at which volume means at this particular point, yes, volume of a gas volume of a gas becomes equal to zero. Volume becomes means you will not find means gases ceases to exist, means there is no existence of a gas rather. Yes, so here at this particular point 0 Kelvin or minus 273 Kelvin, gases ceases to exist. There is no volume of any gas. Got it? So how do I do this? How do I understand this? I understand this by calculating or knowing the relationship, that is nothing but Vt is equal to V naught plus V naught by 273 plus 0.15 into T. This is the formula which is already derived. So I'll further make it V2 is equal to V naught into 1 plus, because I'm taking V naught common, 1 plus T by 273.15 into T. Okay, already T I have written. Further, V2 is equal to, I'll take LCM, I'll be getting V naught 273.15 plus T by 273.1. So what are all these, mom? Yes, Vt is volume of a gas at T degrees. At T degrees. This one. What is V0? V0 is a volume of a gas at 0 degrees centigrade. At 0 degrees. That means at when you convert the temperature of a particular gas to V0, that is a 273 Kelvin, 273 Kelvin, sorry, 273 degrees centigrade, the gases become, but the volume of the gas becomes zero completely. That is called absolute temperature. Yes. Absolute temperature is nothing but minus 273 degrees centigrade or 0 Kelvin, where the volume of the gas becomes completely zero. Got it? Yes, students, that is your Charles law. Okay, now let me teach you Gay-Lussac's law. Gay-Lussac's law is also called as PT relationship. I call this as PT relationship. Okay, now let's see. What does it say? Definition, it says at constant volume. So you're keeping the volume what? Constant. Pressure of a gas. Pressure of a gas is directly proportional to temperature. The pressure of a gas is directly proportional to which one? Proportional to temperature. Pressure is directly proportional to temperature. Take out proportionality. P is equal to K into T and P by T is equal to K. So this is one Avogadro's law, Gay-Lussac's law, and this is also one more Gay-Lussac's law. So further, before I go to the representation, before I do the glacial, see here, we very well know P by T is equal to K, correct na? So if I take two different gases, see here, P1, V1, P1 by T1 is equal to P2 by T2. This is one more formula for Gay-Lussac's law. Yes, students, so what are you keeping constant? What are you keeping constant here? Volume, number of moles are kept constant, and pressure. These three, not pressure, volume, number of moles are kept constant here in Gay-Lussac's law. Got it? Yes, these two are kept constant. Right. So when I see the graphical representation, see here, I am drawing a graph P versus T. Just now we said P is directly proportional to T. Suppose if pressure, see we very well know, P is directly proportional to T. When pressure increases, temperature increases. Pressure increases, temperature increases. So you will be getting a straight line passing through the origin. This is called isochore. Why? Because you're keeping volume as constant. When volume is kept constant, you call this as isochore. Same thing if you're drawing pressure temperature graph for different volumes. You're getting one more graph, one more graph, one more graph like this, where V1, V2, everything is passing to the origin. Students, don't get confused because I'm drawing with my writing pad. V3, V4, same story. See here, P is equal to KT. What is this? Y is equal to mx. Right? But that's a slope. K is a slope. M is a slope. This is the slope. Now, PV is equal to nRT. P is equal to nR by V by T. So what is happening now? What is happening? V is in the denominator. What did we say, students, earlier also? What did we say? If the slope is increasing, now what are you comparing? You're comparing P is equal to K into T. Slope you're comparing with nR by V. Correct? Na? Slope, this slope you're comparing K, you're comparing with nR by V. So what is it? I said when slope value increases, volume decreases. Correct? Na? According to nR by V in the denominator. That means V3 is greater than V2 is greater than V1, or V1 is less than V2 is less than V3. That's all according to this point. Got it? Sure. Right, students. Now let us do one more Avogadro's law. Avogadro's law is called VN relationship. Volume number of moles relationship is Avogadro's law. Got it? Alright. Let us see the definition. What is this? Under similar condition of temperature and pressure. What is this? Under similar conditions of temperature and pressure, you're keeping temperature and pressure similar. Equal volumes of all gases, what do they contain? They contain equal number of molecules. Let us see one example. Equal number of molecules. Okay, right. Let us see. For example, okay, I don't have space. I'll make it here. See here. What am I doing? I'm taking three different or four different gases. What did I say? V is directly proportional to N. Correct now? Yes, V is directly proportional to N. That means in the first one, I'm taking oxygen gas. Second one, I'm taking hydrogen gas. Third one, I'm taking nitrogen gas. Right? Volume should be same. This is 100 ml. This is 100 ml. This is also 100 ml. Everything. Correct? Right? Yes, students. So all volumes. So this also contains the X moles of this. This also contains X moles of this. This also contains X moles of this. So the volume is taken equal means it contains same number of N is nothing but X. Basically this N is X. N is this. If the volumes are same, they contain same number of equal volumes contain same number of molecules. What is kept constant? Sorry, temperature and pressure are constant. Both are kept constant in this. What is student? Yes. All right. This is what it says. Suppose if you increase this, this will also change. If you increase this, this also will change equally. Got it? All right. Next one. Ideal gas equation, combined gas law. Now we are going to combine Boyles law. We will combine Charles law. We will combine Avogadro's law and Wright. What is Boyle's law? V is directly proportional to P at constant temperature. Volume is directly proportional to T at constant pressure. Volume is directly proportional to N at constant T and P. Combine all. So I'm combining. What do I get? P is directly proportional. All V's are there, na? V is directly proportional to N, directly proportional to T, directly proportional to 1 by P. So take out the proportionality constant. V is equal to R T or N T N by P. Rearrange it. You'll be getting PV is equal to nRT. PV is equal to nRT. Right. So I'm writing ideal gas equation is when N is equal to 1 mole, PV is equal to RT or nRT is the ideal gas equation. This is nothing but combined gas equation. Got it, students? Further, same. If I take here, see here, PV, you wrote 1 mole, ma'am. So should I write N here? Okay, let us not write N here so that it will not confuse you. Right. Now see, when N is equal to 1 mole, PV is equal to RT. So PV by T is equal to R. Correct? So now I'm considering two gases. P1 V1 by T1 is equal to P2 V2 by T2. So here in combined gas law, what is the concept? Conclusion. PV by T is a constant. Done? Yes. Suppose before I learn the kinetic theory, suppose if I have to write ideal gas in terms of density, you're going to write ideal gas in terms of density. How are you going to write? Check here. See here. N is equal to number of moles is equal to given mass by molecular mass. Yes, right. So we will write PV is equal to nRT. So PV is equal to small m by capital MRT. Done. Right. This is one more formula. Now see. Shift this. Take this P here. V cross multiply M by V, RT by capital M. Done? Yes. Now take out this capital M outside. Take out this capital M outside. I don't have place. I'm writing it here only. I'll write. Okay, I'll write here only, students. Hope I'm not covering the picture. Yes. So capital M is equal to dRT by P. How did you get this, ma'am? Mass by volume is nothing but density. So M is equal to combined gas law density formula. M is equal to dRT by. This is one more formula in terms of density. Got it, students? Yes. Now let us learn the last topic, kinetic theory of gases. So in terms of ideal gas and real gas, we will see. So kinetic theory basically was proposed by Bernoulli and developed by Clausius and Kelvin, and it was explained by Maxwell and Boltzmann, and it is also called as dynamic particle method, a microscopic model. Now let us learn something, what actually is an ideal gas, what actually is a real gas. Let's see. Ideal gases are those which obeys all gases, all gas laws. What gas laws? Like they will obey Boyles law, they will obey Charles law, okay, they will obey Avogadro's law, they will obey Gay-Lussac's law, lag law. At what conditions? At all conditions of temperature and pressure. At all conditions of temperature and all conditions of pressure. This is what they're going to do. But when it comes to real gases, they do not obey, all gas laws. This is what is real gases. Let us see some examples. So kinetic theory will talk about the difference of ideal gas, real gases and everything. Right. Except they do not accept at. If you create a low temperature and if you create low pressure, not temperature, students. If you create low pressure and if you create high temperature, then the ideal gases, the real gases behaves like ideal gas. Otherwise they are not. For example, like hydrogen, oxygen, nitrogen, carbon dioxide, methane, these are all, chlorine, these are all what gases? Real gases. At what temperature they will not participate, they will not um, all remaining all temperatures rather, right? All temperatures and pressures they will not. But if you create low pressure and high temperature, they are going to behave as ideal gases. Let us see a graph. See here. So, so see this graph. You have basically pressure volume graph, correct? So what are you observing? This is your low pressure, okay? This is your low pressure. Low pressure. See this point. So I have I'm comparing between real gas and ideal gas. Observe. I said at low pressure, what is going to happen? Ideal gas and real gas behave similarly. Real gases behave similarly at low pressures. Slowly you're increasing the pressure. You're increasing the pressure. What will happen, students? See here. Real gases and ideal gases, if you see, ideal gases volume, you see, compare here. At high pressure, I am dropping one line down. This is ideal gas volume. And I am dropping one line down. This is real gas volume. This is for ideal gas. This is for real gas. Now see, at high pressures, what is happening, students? Ideal gas volume is less than real gas volume, right? That means what? Ideal gases will occupy more volume at high pressures. Yes, they're going to occupy more and more volume in the room at high pressures. That is what they're saying, right? So, one important thing, if you remember the concept just now I said, at low pressure and at high temperature, remember students, this is what is important. Real gases and ideal gases will behave similarly. Got it? So we have taken one graph, okay, PV versus P. So we have considered different gases. We have observed, this is the graph which we have got. So this is the ideal gas which we take it as a standard, and we have observed that few gases have got negative slope, means negative graph. You're getting a values below the standard line. Few gases are, you're getting a line above the ideal gas, both negative slope and the positive slope, both negative and positive. How do they behave? How are they differing? You're getting positive also, you're getting positive deviation also for few gases, you're getting negative deviation also for few gases. So why is this? So these are all the real gases, whatever are there, these are the real gases, and this is the ideal gas. So the real gases are showing two types of deviations. One is positive, one is negative. How do you understand this? I understand this with a concept called Z factor. What is this? Z factor is nothing but compressibility factor. What is this factor? Compressibility factor. Now, I said, suppose if Z factor you're getting value more than 1, then it shows the gases show positive deviation. If the real gases Z factor is more than 1, positive deviation means what? The gases which have Z factor more than 1 means they are less compressible. I can't compress them because the Z factor is compressibility factor. They are less compressible. Suppose if you're getting factor Z factor greater than 1, the curve would be negative deviation. Negative deviation below the standard one. They are more compressible. Those gases are more compressible. That means the gases, let us go back again. These gases which are below, which they got negative deviation, for them the Z factor is less than 1. I can compress them more compress. You can compress them more, like your methane gas, CO, carbon monoxide gas. The one which are here, Z factor is more than 1. They are less compressible. You can't compress them. You can't compress them much because the Z factor is more than 1. Let us see the graph. Same thing. See this. See this. Z is equal to 1 for ideal gas. Z is less than 1 means those are negative deviation graph gases. Just like your oxygen, nitrogen, methane are negative deviation. Like gases like hydrogen, helium have positive deviation. They have positive deviation after some time, not initially. First they have negative and then they have got to positive deviation. See here, first they have negative, then they have got a positive. We'll see why. Hydrogen, this is completely positive because they have Z value greater than 1. So we will see why certain gases from negative they are going to go to positive. Let's see. So what is important, students? Let's see the different values, why they are going there, taking into effect of pressure and temperature on deviations, right? There were two types, one is positive, one is negative. Why it is happening? Why positive, negative? Let us see, positive, negative. Let us see both the graphs. Why it is going like that? Why it's showing positive? Why it is showing negative? And come back. First graph. I'm taking one graph. See here. Here what is happening? This is your pressure graph. At low pressure, the pressure is 200 atmospheres. So what is happening, students? At low pressure, yes, low pressure, when Z value is 1, see here, when Z value is equal to 1, right? First, I'm taking this, that real gas is behaving at this point like ideal gas. Correct? Na? Real gas when Z is equal to 1, real gas is behaving like ideal gas. Am I right? Easy. Right. Now, for carbon dioxide gas, we'll see. For carbon dioxide. So, on carbon dioxide, what is happening? You're increasing the pressure 200 to 400, 400 to 600, 600 to 800. You're increasing the pressure. See here, corresponding to this. See here, you're corresponding to this graph. Say this. See the graph. So, what happens for carbon dioxide at high pressure, very high pressure? Z value is becoming less than 1. So, what is happening now? When Z value is becoming less than 1 means, I just now said, na, less than 1 means you can more compress it. When it is less than 1 means more, like you can apply more pressure, more compression. Then compress the gas more. Then what will happen? Carbon dioxide gas will get converted to carbon dioxide liquid. That's all. Easy. That's why when you're compressing it from gas, it is becoming liquid. What is true? That's why it is going up. Further graph B. Now what are you doing? You're taking under pressure, more pressure, and now you're considering temperature. At high temperatures, what will happen, students? At high temperatures, the ideal gas and the real gas, they start deviating. See here, at high temperature, 200 Kelvin, 500 Kelvin to this one. So the values of deviation, they become more positive, they are going beyond the ideal gas. See here, the negative thing decreases and they become more and more positive. Got it? So what is making them, what are the causes for this deviation? So we are going to see one concept called causes. Causes for deviation, why they are getting deviated. This is very important topic, very important topic. See here, let's see. So before that, let me take that and explain. So this causes for deviation, what is it? See here, I'm putting a line and understanding. Van der Waals, let me erase the students, let me little bit space I want. Okay, I'll put the heading on the above. See here, I'm putting causes of deviation. Why they are deviating from ideal gas? Causes of deviations of what? Of real gases from ideal gas. From ideal gas. Why they are deviating? What is making them give negative, positive and negative graphs? See here. Van der Waals has pointed out this. Van der Waals was a person who has pointed out this. What he said, whatever volume, suppose I take this as a container. Yes, this is a total container, correct? Right. Now I am considering a gas. There is one gas. Yes. So when I see this gas, it diffuses, this diffuses, this diffuses, this diffuses, this diffuses. Now he said, volume occupied by a gas, volume occupied by a gas is negligible compared to total volume of the gas, compared to total volume of gas. The volume occupied by the gas is negligible compared to the total volumes of the gases, right? This is first point he said. Second point he said is, whatever forces of attraction are there between the gas molecules, they're negligible. Forces of attraction between gas molecules are negligible. That means this gas molecule is far, this gas molecule is far, this is far, this is far. So because of these two, what happens is you are creating high pressure or low temperature, like the factors rather, right? So when you're creating a concept of high pressure and low temperature, what is happening? The pressure of a gas, whatever is there, will become at high temperature and low, listen, the pressure of the gas, high pressure and low temperature, pressure of a gas is inversely proportional to volume, correct? And the pressure is increasing, volume decreases. So volume is comparatively less than the total volume. Same thing when you're creating low pressure and high temperature. Yes, high temperature means more and more gas molecules are there. Yes, they move, right? Let me again tell you. When I create high pressure and low temperature, what is happening? The volume of gas is less because total volume, how much it occupies. Yes, compared to the total volume, the gas volume is very less. Suppose if you are creating low pressure and high temperature, what is happening? The gas particles start moving. Intermolecular forces will become more, forces will become less. Intermolecular attractions will become less. The gas starts moving and moving. So because of both these conditions, here in this case volume of the gas is less, in this case volume of the gas is more, because the attractions have become less now. High temperature means the gases will move far. Because of these two factors, high pressure low temperature, low pressure high temperature, here volume of gas is less. In this case intermolecular forces, IMF forces, are less. Intermolecular forces of attraction, intermolecular forces of IMF or intermolecular forces of attraction are less. Because of these factors, there is deviation, positive deviation and negative deviation. So to create or to correct this, he has given one correction factor. Okay, he has given one correction factor to us with the units we will study. He said always to correct, in order to make, because in order to make real gas, or in order to make ideal gas and real gases to behave equally, you should always do two things. One is volume correction, and you should do volume correction, and you should do correction due to, one is volume correction and correction due to intermolecular forces. Correction due to intermolecular forces. Two things you have to always do: intermolecular forces. So you have to do these two corrections, then your problem will be solved. Yes. So he said, yes, what did he say? He always said ideal volume, or the free space, whatever is there. Okay, the free space, whatever is there. Yes, he said, careful students, note this point: free space, whatever is there in the particular container, is less than observed volume. So V ideal is equal to V minus B. The ideal volume left is less than the original volume. This is what is said for the volume correction. So for n moles, V ideal is equal to V minus NB. This is one correction of volume. This is one formula for correction of volume. And then for intermolecular forces correction, he said one thing. What is that? Correction due to intermolecular forces. Correction due to intermolecular forces. What did he say for this? He said at high pressure, you very well know pressure At high pressure, what will be less? Volume is less. Correct? That means P is inversely related to 1 by V. Correct? So, this particular pressure, whatever is there, is where is it high, students? Where is it high? It is the pressure on the walls is very high. Correct? When the pressure is high, if you take this walls, this gas molecule is here, this gas molecule is here, this gas molecule is here, here. The pressure on the containers is more. I mean, on the walls is more. So pressure on walls is more. Correct? Na? So what did he say? P total is equal to P plus AN square by V square. He has given one total formula for correcting the intermolecular forces of attraction. And he said, according to this, P plus AN square by V square, that is intermolecular force correction, is equal to into V minus NB is equal to RT. Earlier, what did we write? We have written PV is equal to nRT. Correct? So instead of this, he said, please correct it. For pressure, take this correction factor. For volume, take this correction factor, make it to nRT. What are A? A and B are nothing but van der Waals constants. Van der Waals constants. And the units are given here. So this is the pressure correction factor and this is the volume correction factor. Right? Right. So this is your complete chapter, students. Wow. We have completed the chapter 100% states of matter. Right? 100% states of matter in one shot. Got it, students? Right? In one shot. My request to all of you, please like the video, share the video, comment the video, subscribe the video. Thank you for watching. WC has done 1600 plus videos. Yes, for grade 10th, 11th, 12th, JEE students and NEET students. So please subscribe, share the channel. It is for free. Thank you. Thank you so much for watching. Bye-bye and happy learning, students. Happy learning. God bless you. My request, please share the video to all your friends. Like it if it's possible. It took a lot of time for me to do this. Thank you.